Okay, so now it's recording. I don't know if that'll stop. Okay, looks fine. Does it still say recording on like somebody's screen?
Yes.
Okay. All right. So yeah, welcome to the Huff Basics presentation. In this presentation, I'm not going to be going into every little thing in the language. However, we are going to be getting fairly deep. We'll be looking at some code, and I'll try to go over the basic syntax, the language design rationale, and development practices. And then we'll spend probably about half the presentation looking at some example code, and I'll be explaining what it does and why, and all that sort of thing. So first thing to cover is what and why is Huff. It is a low-level language, very similar to Solidity assembly. It uses opcodes pretty much directly with some extra little bits and pieces. It is written by the Aztec protocol guys. They're trying to develop like cryptographic libraries on Ethereum. And they developed this as part of like an efficient elliptic curve library. So they really wanted to get efficient elliptic curve calculations onto the blockchain, and they did it via Huff. Of course, since it is able to be put on the blockchain, it compiles to EVM bytecode, and you can deploy it as a contract. It exists for gas cost optimization, and the main difference between just writing your code in Huff versus writing it in like assembly or opcodes is that it uses macros, and those macros allow for like unit testing of what are effectively functions. So you can break a really big program down into its different macros and test those individually, and that way you can get some finer granularity on your tests. And over on the right side of the screen, we've got some Huff code, but don't worry about that too much. We'll get into it more. Those are just, like each one of these looks like a function definition. It's a macro definition. Yeah. So one thing we need to talk about before we really get into Huff is the stack. Is anybody not super familiar with the stack, or is everyone relatively confident with their understanding of like what a stack is?
I'm good.
Okay. Well, then I won't spend too long on this because no one said that they really don't know, but Huff deals directly with the stack. All of the operations in Huff will use items on the stack and then add more items to the stack potentially, or potentially take items off the stack. But there's no concept of like, you know, using a variable inside of a function, like passing a variable in, like that doesn't exist. Like everything you do is going to be with whatever's at the top of the stack. So it's very important that you make sure to manage your stack properly and keep track of what's going on with it. And of course, remember that it's always the stack. There's no jumping around in memory with Huff, or at least not easily. So the key features, like I mentioned, there's macros instead of functions. They're essentially analogous to functions. There are template parameters instead of variables. So I know I already said that there's no such thing as variables, and this is kind of true, kind of false. Template parameters are like, they're like input parameters for a function, but basically what they allow you to do is name some piece of memory, and then you can push that to the stack later, and that's a template parameter. And then they, instead of using ifs, switches, for loops, while loops, whatever, Huff uses jump labels and jump tables and what are called packed jump tables. And in this presentation, we'll get into jump labels, but I'm not going to really touch on tables or packed tables. But this really impacts program flow. When you think about it, a lot of program flow relies on if statements, else statements, switches, loops, etc. These need to be constructed and thought about differently in Huff. So that brings me to my next slide, which is thinking in Huff. Macros are a lot like opcodes. Every opcode will potentially take some items off the stack and add some items to the stack. Sometimes it'll add 0 items to the stack. Sometimes it might take 0 items. I'm actually not sure if that's true, if there are any that take 0 items, but macros are the same way. And in a macro definition, if you look at the bottom of the slide here, on the right side of that macro definition, it says takes 2, returns 1. So it will pop 2 items off the stack and then push 1 item onto the stack. And macros, because they're a lot like opcodes, can be used in line the same way that an opcode might be used in line in Huff. Other important things to point out, there's no typing in Huff. So all data is interpreted like literally as a uint. So if you have things like addresses, you might have to do careful inspection of them to make sure that they don't have like 21 bytes of data that's non-zero, because addresses are only supposed to have 20 bytes of non-zero data. And of course, there's no variables, there's no mapping, and there's no events. All of these can kind of be constructed. Like you can get things that behave similarly to macro or to mappings and events, but you know, it's not an easy thing to do. And function selectors are handled manually. This is a big deal. Whenever you call like a smart contract that is written in Solidity, sort of the handling of function selectors is done kind of implicitly. Like whatever function you're calling, 4 bytes of data will be at the beginning of your call, and then the EVM will find, you know, the correct function that matches those 4 bytes, and you can start performing operations like using that function or whatever. But in Huff, you have to create what's called a main function that will then make, well, a main macro, I guess, that will then like make the calls to the separate things that you're trying to do. And you have to like take those 4 bytes that are the function selector and like manually, you know, go through and determine like, okay, what's this guy trying to do and where should we take him in the program based on this. Again, you know, jump destinations are used instead of ifs. You're going to see a lot of jump destinations in this presentation. And whenever you have constants, which there's a definition for a constant right over here, it's just a macro that returns 1. And you're going to have to use constants for like, if you want to store memory in a certain spot, like in storage, I guess, yeah, you'll have to like name that spot in storage, and then you can call like the name for that spot in storage, and it'll return like the actual spot, and then you can store data at that spot. But it's kind of a convoluted way of storing memory, so it's something to keep in mind as well. Okay, so I want to touch on template parameters. Like I said earlier, it allows you to just name a piece of data and then push it later by using that name rather than the value of the data. This is really valuable if you want to reuse code. You can use a template parameter and just treat it as like, say, you know, like if you have an add operation that you've created, you could treat one of the inputs like, you could say like, okay, like the first input is going to be a template parameter, and then you can pass whatever in as that template parameter, and you can reuse the add there. It's not the best example, but it's the only one I can think of right now. But we will see more template parameters, don't you worry. They're really good for passing jump locations, and we'll see that mostly. They're kind of the closest thing you'll get to a variable, and importantly, they have these little pointy brackets, or whatever you call them, triangle braces, and that's how you know it's a template parameter rather than something else. Okay, style guidelines. This is a big messy slide, but macros are capitalized. We'll see that later. Like I said, with template parameters, error destinations and just general jump destinations, it's pretty standard, it seems, in Huff to pass them as a template parameter whenever you make macro calls. Of course, reducing gas costs is the point of Huff. So when you're writing in Huff, there's a lot of different ways to do things, of course. However, you should be always picking the one that has the cheapest gas cost. And you can always consult the Ethereum yellow paper or I believe there's like a gas cost per opcode table floating around somewhere on the internet. You can use that to determine what the best way to implement whatever functionality you're trying to do is. And of course, tracking your stack with comments so that you don't lose your mind while writing Huff. Over on the right side of the slide, there's this example code with 2 highlighted is0 opcodes. So this is kind of like where Huff shines. The Solidity compiler might actually create something that does this with all these opcodes, and it'll have 2, is0 opcodes in line with each other. And you'll notice these is0 opcodes come right after a greater than opcode. So the greater than opcode will return a 1 or a 0, and then is0 will flip that, and then the next is0 will flip it again. So we can make it more efficient by removing those 2 is0 opcodes. And when you start constructing logic in Huff, you'll find that stuff like this comes up a bit. And down at the bottom of the screen, there's just an example of error destination passing. I cropped these images and they're maybe a little confusing, but the top line where it says template error location, that is the line above the macro definition where this is being used. And so it creates a template parameter called error location. And then the line below it is actually a line of Huff code inside the macro. And you can see that error location is being used in line. When you see that, what it means is that whatever was passed in as the definition of error location is just getting pushed to the stack when it hits this error location, thing in the inline code. Does that make sense so
Hey,
far?
Eric,
yes.
Why does it have 3 OR statements in there?
So each one of those ORs is going to consume 2 opcodes and, consume 2 items on the stack and return 1. And in this case, I believe there's 3 items on the stack that all need to be ORed together to produce 1, or I guess maybe 4 items on the stack to produce 1 item at the end. And then that will be used with that jump I that you see at the end to determine whether the program needs to jump or not. We'll see another
it's
thing.
An OR.
Yeah.
It's an OR with a lot of parameters.
Mm-hmm. Yeah, exactly. It's just like a 4 input OR that has to eat up all these items on the stack.
I have a quick silly question. Does execution happen left to right or right to left?
Oh, that's a very good question. It happens left to right.
Cool.
Okay, so we're going to look at a macro. This is a very simple macro. So you'll see at the top, it's got this template parameter. And then over there, it has the takes 0, returns 0, statement that just kind of describes the behavior it has, relative to what it does to the stack. And yeah, template parameters. You'll notice that the template parameters aren't included in the takes. That's because they aren't consumed when the macro happens. You're not pushing the template parameter to the stack. You're just naming it something and then possibly pushing it to the stack when you call it inline. So down below, this is an example of a call to the macro that you see defined here. And you'll see, there's the name of the macro, utils not payable, and then it passes in a template parameter, and it just happens to be called error location in both spots. But I believe you could, in this call to the macro, you could call it like foo, and then it would be renamed error location in the context of the utils not payable macro. And then there's this, the body of the macro. What does it do? I can tell you. It pushes the call value to the stack, which is the amount of ether that's being passed with the transaction itself. And then it pushes error location to the stack. And then if call value isn't 0, this jump I is like jump if. If call value isn't 0, the jump will occur and it'll jump to error location. So what this thing is effectively, a non-payable fallback function. So it'll revert or go to the error location, which I happen to know causes a revert if you try to send any ether in. Okay, so here's a jump label example. So you'll notice in the inline code, we've got isOwner right there. And because this doesn't match any of the opcode names, Huff will automatically assume that it is a jump label since it also doesn't have the pointy brackets. And then we've got our jump I, and we've got this isOwner with a colon over here, which is like the destination of the jump label. That colon tells Huff, like, okay, like this is where to go if you jump to this jump location. Notice that the label has nothing under it. Execution will just continue from wherever the call to utils only owner, which is the macro we're looking at, from wherever that happened. So what does this code do? Basically, it compares whoever called the function to the value of owner, which is stored at owner location, as you see in this first inline code piece. It compares it to see if it's equal, and then if it is equal, it jumps past this 0x00 revert line and continues execution. However, if it's not equal, it won't jump, and then it will hit that revert, and the call will revert. Okay, so now we're getting into even more fun. So this is an example including jump labels and template parameters. I'll run through it a bit quickly because we'll be looking at this more later on in the presentation. So inside ERC20 underscore main, which is this thing on the left, this whole deal, that's a macro. It makes a call to ERC20 double underscore function signature, and it passes in a long list of template parameters. And those template parameters are actually jump labels. It's quite confusing, but you'll see like this transfer being a template parameter on the left. It corresponds to this jump label transfer with a colon down below. So it makes a call to the ERC20 function signature macro. And then from there are a bunch of jump I's. So presumably, if you're making the call correctly, one of these jump I's will be activated, and it will jump to this error location, which was passed in as a template parameter. So it'll jump to whatever the value of this template parameter is, which just happens to be an error location that, or a jump location that was defined in the other macro. And this is an important thing to note because jump labels do not necessarily have to be within the same macro that they're like activated in.
This is interesting. It looks like, so you can specify the order in which the functions are looked for.
Yes.
So like, exactly. So you could, it sounds like you can like, functions that you think will be called more often, you can put higher in the list, so they'll take less gas on average to find them. Whereas,
Yes.
as I think was Solidity, if I remember correctly, they do a similar thing under the hood, except you can't choose the order. They go like alphabetically or numerically according to their the function signature. Is that correct?
Yeah, actually, and like I mean, I don't know about Solidity under the hood, to be frank, but definitely as you move through this Huff like macro here, trying to figure out where you're going to go based on your function call or whatever, you will burn more gas as you move down the list. So you can optimize for very frequent calls by putting them at the top of the list. I would also say that you might be able to optimize for like view calls by putting them at the bottom of the list, just because, like, you know, who cares? So this is from the last slide. It's that thing that was on the right side of the slide, but we've zoomed in a little bit and we're going to go more in depth. So this first line, it loads the call data at spot 0, and it's going to load 32 bytes of call data. So that 0x00 and call data load will be doing just that, first 32 bytes of call data, and then it shifts it to the right by 224 bits. And what that ends up doing is it leaves only the first 4 bytes of call data at the end of a 32 byte long word in memory, and those 224 extra bits are just going to be zeros. So what you're left with is just the function selector, and that'll be at the top of the stack, and it says function signature here in comments. That's a stack trace, just letting you know, like, this is how you get the function signature. So now our stack only has the function signature on it, and then we each line duplicate it once, and then these are like literals that are pushed to the stack. So we're duplicating it, and then we push a literal with these values, and then we compare them. And then if they are equal, we jump to the correct destination accordingly. And as Austin pointed out, more gas is burned as you move down the list, so you can optimize if you have really frequent calls that are going to be happening, put them at the top of the list. And then this last thing we actually saw earlier, utils not payable. It'll revert if your call value is non-zero. So it'll hit that. And then if somehow it makes it past that, I guess it just does this return thing, and that 0x00 has to do with the message that you'll get on the end of execution. So now we're going to look at what happens when you do an ERC20 transfer. And thank you guys for patiently sitting through all of this. This is the last big code section of the presentation, so bear with me here. So we've looked at this code quite a bit in the last few slides, so I'll just quickly go through it. Every contract call starts here to this main function, and from what I can tell, that main function is just going to be, or the main macro, I keep saying function, it's going to be the last macro defined in your Huff file. So it'll go there automatically, and then it'll start like by calling this sort of function selector handling macro. And then from there, it'll jump to the location you've defined. And so since we're doing a transfer, we're going to jump to this transfer label, and then it's going to call ERC20 transfer with the template parameter throw error. And you'll notice that down here, throw error is gonna do a revert for you. So if you ever jump to that location, it's going to revert, and we can just pass it along to every macro in the call chain so that they all jump to the same spot. Okay, so this is what the ERC20 transfer macro looks like. We're going to go through these first 3 macro calls in order. Let's go. So the first macro call is transfer init, or ERC20 transfer init. The first thing that's going to happen is it's going to load the 3rd word of call data. So this 0x4 will load the 64th byte down to like, I'm not exactly sure like if I'm saying this right, but basically it will load the address that we're trying to transfer from, I think. Yeah. One of the addresses.
An address is smaller than the word size here, so you have to mask it.
Yes, that's exactly what's happening. So this address mask down here, you'll see at the bottom of the slide, we've got 0x00 and then a bunch of Fs, which are just ones in hex, and then and. So it will and the 32-byte word at the top of the stack with this word that is a bunch of zeros and a bunch of ones, and it effectively chops off all data past the 20th byte, so that we know that our address value is actually like correctly set up. It's not going to be like a 22-byte long address, for instance. And this is one of the things with Huff, like there's no typing, so Solidity would handle this for you, but Huff doesn't, so you got to handle it yourself. And then I won't be covering it in this presentation, but because we're doing an ERC20 example, it has to match the spec, and so it has to emit events. So these lines just deal with event stuff. Basically, transfer event signature is a constant that will push like the value of the event signature. I'm not totally sure how events work, so I won't dive too far into it, but then these other two values have to deal with that. And you'll see at the end of this macro, we have a stack trace showing you what the stack will look like at the very end of execution. And the top of the stack is on the left, just for reference. So we've got our to address, our from address, the signature, which is the transfer signature, by the way, and then this X20, or sorry, the event signature, not like the function selector, but it's the signature for emitting an event. And then this stuff for the event, and then the value that's being transferred. Okay, so now we move on to the next piece. It's just the next function or the next macro that gets called in the transfer thing. So this is transfer give to, which handles adding to the balance of the recipient. So when ERC20, functions or ERC20 contracts are implemented in Solidity, there's a mapping that keeps track of everybody's balances. The mappings, they're basically hash tables where you hash some data, and that is like the key at which somebody's balance is stored. So they do it here manually. They create a key for balances of the recipient, balances to, and then this chunk of code, it loads the value of balances to, adds the new value, checks for overflow with this greater than, and then importantly, it does not revert if it overflows. It just keeps the overflow value as like a flag, so that greater than pushes a 1 or a 0 to the stack, and it'll keep that flag, and it'll be used later to decide if we should revert. But for right now, it's just going to continue execution. And then it performs an store to, put those balances, or to update the balance for the recipient. So right here, this V greater than V plus B, that's the overflow check. It will be a 1 if there's an overflow. And we'll keep that on the stack to do something with later. And then the next thing that happens is transfer take from, and this subtracts the balance of the user we're transferring from. So we create a key for balances of from, and then we do, balances of from minus value. We store the new balance into that same spot in memory, and then we check for underflow with this less than. And you'll notice now at the top of our stack, after this less than operation, we have error 1, which is that same flag from before for the overflow. And we have error 2, which is a flag for, I guess you could call it underflow, where you've paid somebody more than you actually have in your balance. And this less than is like false, or I guess it's true. Yeah, it starts to get confusing with trues and falses, by the way. But basically, if error 1 or error 2 equals 1, we have a problem with overflow or underflow. Okay, so now we're back into ERC20 transfer, and this arrow shows where we are. So now we hit this OR, and that OR takes those two error flags and ORs them together. So if either one is 1, we're going to be left with a 1 on top of our stack, and this jump I will activate, jumping to the error location and causing a revert. So that's what keeps us safe. But the reverts don't even happen until here. And then the rest of this is just event stuff. We don't care. And now we will be looking at the costs of all of these different, methods, macros, functions, whatever you want to call them. Basically, the Huff guys or the Aztec guys looked at the gas costs for all of the different methods you can call, and in Huff, all of them cost less, which is pretty cool. Here are some resources for Huff. There's the Oliver library and the Weierstrudel library by Aztec. They just implement different elliptic curve calculations very efficiently. Weierstrudel is just trying to make a precompile that already exists in the EVM more efficient. And they actually have a really cool graph in their repo where the precompile, I think, only does 1 point at a time for this computation. but Weierstrudel does up to 16. And the more points you include, the more efficient it becomes on a per point basis. Also, something really nifty they do with Weierstrudel, which I think is really cool, you have to send exactly one way with your call to this, and they use the value, like they use call value as a value in the calculation. And that helps save gas costs somehow. So they don't have to like load or like name a variable. They can just load the call value, and they use the number 1 a ton in their calculations. So that's kind of nifty. It's a neat little trick that you can do with Huff. Proxies.huff, thanks to Andrew who found that. This guy, Nick Ward, created some really efficient proxy contracts in Huff. Some don't have any loads or stores. And I mean, if you ask me, that's like really cool because that's going to be the most efficient contract you're basically ever going to see on Ethereum. And then there's the Zero to Nowhere series, which all of my code snippets came from, where they walk through the development of the ERC20.Huff contract. So the current state of Huff, it's still in development. There are some more planned features like bytecode tables that haven't been implemented yet. And Nick Ward, I know, has patched Huff because something wasn't working, I guess, with his proxy implementation. I haven't delved super far into it, but obviously there's a need to do some of your own patching. So developing on Huff is still a little rocky at this point. Security considerations, typing is a huge thing. Like we saw with the address mask, it'd be super easy for you to not have that address mask and for you to pass in an invalid address, which you would never want to transfer funds to an invalid address. Honestly, something that's really cool about Huff is that because you have to declare where storage is happening basically every time, you have to do like an store to a location. If you're careful about how you manage your locations, you may never have the issue that Solidity has, where you could have storage location overlap with like upgradable contracts. So that's really neat if you ask me. The logical checks can get confusing very fast. It can be difficult to keep track of whether something should be a 1 or a 0, or if you have like a very long logical string and you need to invert the output, that can get confusing. Boolean logic is super fun, as many of us probably know, but if you mess up somewhere, you could have some issues. And you have to understand how the EVM memory structures work. Back when we were looking at the construction of like a mapping key, you have to understand like how the SHA-3 function behaves inside memory, and it actually uses the first 2 words in the EVM's memory and does like a hash on those. So if you don't like know that and you're storing memory at those locations, you could get some bad side effects happening. And of course, the language is still in development, so things could be broken and we might not even know it. So that's another consideration. Leo asked me to look at Yul, and the TLDR is Yul is a lot like Huff in that it uses like opcodes, but it doesn't really, Yul doesn't really deal with the stack. Yul still has syntactic sugar like variables and loops to help with program flow, and those all have implicit things that are happening under the hood that make Yul slightly less efficient than Huff, and Huff needs to be as bare bones as possible. So certain things like declaring variables you can do in Huff, but in Yul it will perform a little bit more than just like a single opcode operation to do that. So yeah, that's about it. Does anyone have any questions?
The comparison with Yul, is there a comparison in terms of gas, like coding the same in Yul, like for instance for the ERC20, the one you showed with Solidity versus Huff, something like Yul versus Huff?
I mean, I could look at it, but frankly, I don't think there's anything really out there. It's pretty difficult to find resources on Huff as is, so I would guess that Huff is more expensive, or sorry, Yul is more expensive than Huff, but there's not any resource that I could pull up and show you. I don't have firm numbers on that. So yeah, does anyone else have questions?
I'm just impressed with how clear this was. Congratulations, because it's a mess and you made it seem actually cool. So I'm not sure if I should trust you and go into Huff, or it was just your presenting skills.
Agree with you. It's been amazing, Eric. Thank you very much.
Yeah, I'm really glad you guys liked it. Okay, well, it looks like we have less than a minute left, so thank you everyone for coming, and if you think of questions, let me know, and watch out for updates in the future.
Thank you.
Thank you very much, Eric.
Great work.
Bye, everyone.